All right, I'm back. This is exciting. How are you, Lucia? Welcome to my stream. Today we're going to be solving the biweekly contest 124. Here's the link. Let me pin in chat. Nice. And let's get started. So Q1. Let me share the link. So maximum number of operations with the same score 1. So there are two parts to this problem, but we're not gonna worry about that right now. So we're given an array of integers called nums, and we can perform the following operation while nums contains at least 2 elements. So we choose the first 2 elements and delete them. And the score of the operation is the sum of the deleted elements. Your task is to find the maximum number of operations that can be performed such that all operations have the same score. Return the maximum number of operations possible that satisfy the condition mentioned above. And we get 2 examples. Okay, so this is an easy. So it seems like we don't have to, the operation doesn't require any choice. We have to always choose the first 2 elements. So we can just simulate, which makes sense because this is an easy. So here in example 1, we have this nums array, and the score is 5. And so you can perform 2 operations. We got 3 plus 2, so that's 5, of course. And then 1 plus 4 is also 5, so we remove those 2 as well, and then we're left with only 1 element, so we need at least 2 elements to do an operation. And so let's simulate this by removing the elements, but remember that, and notice that the array is pretty small, at most 100, that's why we don't have to do anything too efficient. So notice that if we're gonna removing from the beginning of a list is slow, but removing from the end of a list is fast. So maybe we can reverse the array, and then we can pop the last 2 elements. Okay, so we need nums to have at least 2 elements, and yeah, we're gonna count in res how many operations we've made so far, and then we want to know what the target score is, or the score it's called here. So the score is gonna be defined by the last 2 elements. This is how we sum the last 2 elements in Python. And so here, to perform another operation, we want, again, the nums to be equal to the score. And if that's the case, we perform an operation, which is removing the last 2 elements, which are analogous to the first 2 elements with the reversed array, and we count 1 operation, and we're done. So this should be good enough. We get the examples right. There are no edge cases, right? So there are always 2 elements. So because here we assume that, so it better be true. Yeah, that could be an edge case. Theoretically, you could get an array of 1 element, and that would be on 0 operations. Yeah, I guess this would work, I think, but it doesn't matter because it's not possible. Okay, so let's submit, accepted. Good, good, good. We're warming up. So let's move on to the second element. The second problem, apply operations to make string empty. So we're given a string S and consider performing the following operation until S becomes empty. For every alphabet character, remove the first occurrence of the character in S if it exists. So yeah, so notice that we do like a full scan and we remove the first occurrence of each. So we are removing potentially many characters in one operation. So here in the example, on the first operation, we remove all of these 3. Then in the second one, we also remove 3. And in the last one, so yeah, so we are asked to return the string before applying the last operation. So here, this is the answer for this string. All right, and the string is long, so we probably don't want to simulate the process. We want to do something smarter. So yes, the first idea here. So notice that we can figure out how many operations we will do before that's going to depend on the number of occurrences. The maximum number of occurrences is going to determine how many operations we do, right? Because yeah, if we do less than those, there will be a character left there. So maybe we can find out how many operations we want to do. So let's call this Q, and we want to count the number of occurrences, and we want to get the maximum of the values, right? So this is the number of operations that will make the string empty, but we want one less than that. All right, so now we're gonna be accumulating. So now we know that we're gonna keep track of how many times we've seen some character, and we want to ignore the first Q occurrences of the character, right? So we go over the characters of the string, we count, we've seen C this many times, seen times, and if seen is greater than K, so for example, if K is 1, then we want to skip only the first one. So when we first see C, seen of C is going to be 1, and in that case we don't want to add it, we want to skip it. So when seen of C is greater than K, then we don't skip it anymore, we want to include it in res, and then we return the string of res. Have you been doing the contest still? I couldn't participate on this one. I just absolved it. Oh, so this is Q, not K. All right. Let's see if we got it right. Passes the example. You can see my profile. It's LeetCoach is my username. Okay, so we got it right. That's good. That's good. Let me share my solution in case you're interested. Hi, poor Jewish. How's it going? We're solving a contest. Cool. Yeah. I don't think I shared this one. Let me share it as well. Oh, you're noob. Hey, welcome. So we're done with the first two questions. We're gonna move on to Q number 3. So let me share the link. Maximum number of operations with the same. So this is part 2 of question 1, but notice that it's not exactly the same problem. Here, the operation, here you have a choice. You can choose the first 2 elements to remove, or the last 2 elements, or the first and the last. So you have 3 options here. So this becomes harder. But again, you have every time you delete 2 elements, the score has to be the same. Okay. So notice that here. So remember, I always say this, but you always need to pay attention to the constraints, because the problem can change a lot. So here, how do we read this? So the size is at most 2000, and you have to translate that. That means that you can get away with a quadratic algorithm. If it's around 1,000 or a few thousand, you can get away with a quadratic algorithm, because this is 4 million. An n squared algorithm will be doing 4 million operations approximately. So that's good enough in LeetCode. You only worry if you get to 10 million or 100 million. All right, so, well, that means if we can get away with a quadratic algorithm, so maybe, so notice that here we have choices, right? We have a choice to make. And the score maybe eliminates some of the choices. If it's 10 million, then we can't use, well, no, I mean, if it's 10 million, it's borderline. In many cases you can get away with it, but sometimes you can. It depends on how tight your operations are. But yeah, I mean, most of the times you can get away with 10 million, but you have to pay attention and be careful. So most of the times it's not. Well, that's what I say. The threshold is around 10 to the 7 and 10 to the 8. So if it's 10 to the 7, you can try it out. You can, yeah, and if it's tight, you can get away with it sometimes. If it's 10 to the 8, then it's very unlikely to run in time. You're probably gonna get TLE. So I think in LeetCode, it's kind of hard to give an exact threshold, because I think it depends on how many test cases there are. But those are the rules of thumb that you should use. Okay, so here what I was saying is that maybe the score, since you have to respect the score, maybe the score can eliminate, maybe the first 2 elements don't, maybe the last 2 elements are the only ones that add up to the score, and then you don't have any choice to make. But what happens if you have if they are all valid, then you don't know which one. Maybe you don't know which one is the optimal, right? So, but luckily, maybe we don't have to be smart. We don't have to be greedy. Maybe we can try them all. And notice that once you try something out, then you remove the elements, and so then you have a range of the nums. Once you have removed elements, you have a range of nums, and you still want to maximize the number of operations. So that's what's called, there's an optimal substructure. You get a sub problem which is the same as the original problem. You also want to maximize the operations, and the number of ranges that there are is quadratic, so that would be the number of sub problems is going to be quadratic. So maybe we can try that out with a cached function. So we want the maximum number of operations. Yeah, this is spam. How do I remove this? I don't know. Anyways, okay, so let's go on. So here we want L and R to define our range, and we also want to know what the target is to see if an operation is valid, right? And so the first operation is going to determine the target. So we can try them all, right? So we could say we want the maximum of the max operations, always from 0 to n minus 1. But the target can be the first two elements, right? So this is also has at least two elements, so we're not gonna go over. So we have three options: the first two, or the last two, or the first and the last, right? So these are our three options. We try them all. We don't have to be greedy. And now, so this is the number of elements in the range. If it's 0, no, if it's less than 2, right? Because we need 2 elements to do an operation. If it's less than 2, then you can't do any more operations. Then, so we have, if nums of L plus nums of L plus 1 equals target, then we can do this. We can do the max operations of, so we get the first two, so we increase L by 2, and we add 1. So, and the other option would be the last two elements, so R minus 2, no, R minus 1 and nums of R. Could probably have used Oh, you mean the base case? Yeah, I think this is so so I know that L and R are inclusive indices, and this is the usual way to count the number of elements in a range with inclusive indices. So here we have this, and we want to subtract 2 from here. And then the last option is to get the L and R. And here we add 1 to L and we subtract 1 from R. And we return res. And this should be it. 3 and 2. Accepted. All right. So notice, notice that this is that here, since we're not copying the array, we're not passing an array here, we're only having the range, the limits of the range, then that's why we can cache easily here. Okay, so yeah, so here I think the key to this problem is realize that we can do a quadratic, and that the sub problem. So if we try all possibilities, we're gonna get a quadratic number of sub problems. Cache, yes, the whatever you cache has to be hashable. Right. So yes, a list, since it is mutable, it cannot be hashable. I mean, you can work around that by using a tuple, but the best way here is to just use the limits of the range. All right. So did I? Yeah, I shared the submission. So let's move on to the last one. So this one is a hard. Maximize consecutive elements in an array after modification. So you're getting positive integers, and you can initially you can increase the value of any element in the array by at most once. Alright, so after that you need to select one or more elements from the final array such that those elements are consecutive. So it's not very clear what it means, but yes, you can select. They have to be consecutive in terms of value. So here you have 1, 2, and 3, and you have to return the maximum number of elements you can select. All right, and there are 10 to the 5 at most elements, and the values are up to 10 to the 6. Yes, we have the option. So here it says at most. At most means 0 or 1. So for every element you can increase 1, or you can keep it as it is. So yeah, so here it's suspicious that the values are not the range of the values is bounded. It's not 10 to the 9, for example, that it would make this problem different. So notice that the order of the initial order of the elements doesn't matter, because why would it make it different? Well, you'll see why. Because maybe we can try starting well, no, yeah, you're right, maybe it's not, maybe it wouldn't change it. So notice that if we try to start a sequence of consecutive elements from some value, So we want to see if we can add the current value. So from some x, we want to see. No, I was thinking that maybe we wanted to start a sequence from every possible value in the range, right? And if the range was too big, then it would be too slow. But we don't have to do that. We can be smarter. But let me follow up my train of thought here. So let's say that we're trying to start a sequence from value x. So we need to get value x from somewhere. So we either, and then we were going to move on to value x plus 1 and see if we can get that value and so on. So for value x, we either can get from the initial values the value x that would be sufficient, but we also have the option of getting the previous value, because we could have added 1 to that value and gotten x, right? So if we have an x minus 1, and then we apply the operation, the initial operation, and we added 1, then we get an x. So that's another way to get x. But notice that it is always, since we're going from left to right, it is always better. Okay, you want me to write this down? All right. Let me see. So we're gonna try to generate a sequence that is as long as we can, starting from value x, right? So we're gonna first try to find a next value in our set, then x plus 1, then x plus 2, and so on. So okay, for x, we have two options. We either we look into the initial set. So we either get an x. So if we have an x, then we can use it in our sequence, because we don't add it anything. But we notice that we can also use an x minus 1. If we have an x minus 1 in the initial set, we could add it 1, and then we get x, right? So, but notice that it's always better. We always want to try to use x minus 1 as we can, because when we keep going, when we go to x plus 1, then again we're gonna look into x. If we have another x there, we could add 1 to it and get x plus 1. But we don't care about x minus 1. X minus 1 is already out of the range here. So that's why when we're trying to get our x, we're first going to try to get an x minus 1, and if we can, then we're forced to get an x, right? If we can't get an x minus 1, we are forced to get an x, and if we cannot make any of those, then we cannot make it longer, right? So maybe, and notice that we can have a function, longest, let's call it longest, that given an x, it's going to tell us how long the length. This is going to tell us the longest length starting from x. right? But notice that when we move on to x plus 1, then we have a recurrence, right? So longest of x is going to depend on longest of x plus 1. But there is a catch, because when we are at x plus 1, we're gonna try to get an x at some point. We're gonna see, well, if we have an x, then we added 1 and we cover x plus 1. But maybe we used an x when we were at x. So we're going to add to the state. We're going to remember in the state if we, so how many prev, it's going to tell us how many of the previous element we have already used, which is going to be 0 or 1. Okay, so that gives us a recurrence, and the number of values of x is bounded by 10 to the 6, and this is the prev only has 2 values, so then the number of subproblems is small, it's 2 million. So that's how we're gonna do it. So again, we cache. We're gonna get the longest from x, and we're gonna determine if we have already used a value of the previous value, an occurrence of the previous value. Okay, we want to know. We're gonna know how we want to know how many we have of each value. So let's have a counter. And so here we want to know if, so first we try to use x minus 1, but the count of x minus 1 is however many there were initially minus this value, the prev, because that tells us exactly that. And so if we have 1, if we have more than 0, then we can use that. We always prefer to use x minus 1. So then we do this, right? We move on to x plus 1. So we didn't use x, we used x minus 1, so this is 0. And we add 1 to the longest x starting from. We add the x, right? So here, if we cannot use x minus 1, we try to use x. Why is it 0 here? Well, because here we are using an x minus 1 to cover our x value. So when we move on to x plus 1, so remember that this determines if we use one of the previous value. So here the previous value is x, but we didn't use an x, we use an x minus 1. So that's why this is 0 here. You got it? Okay, so now if we couldn't use an x minus 1, we try to use an x, right? And we check if there is one, and now we use an x, so we use the previous to x plus 1, so we set a 1 here, and we add x to the sequence, and if we cannot cover x with x minus 1 or x, then we return 0. Okay? And now we have to see where are the starting positions of the sequences. So we don't have to try with all possible values. We only have to try for, so for the numbers in nums, we could start at n for every number, or at n plus 1, right? Because n plus 1 would have could use an n from the previous value. So these are the only starting points that make sense. Any other starting point won't have any way of covering that value. So here we get the longest from x, and this is it. I think this one was easier than the, well, I mean, the code is shorter, at least. Accepted. The code is pretty simple once you get the idea. Let me share. Yeah, this is the P. Exactly. Yeah, I mean, it's memoization. So whenever you use cache in this, and you have overlapping subproblems, it's the P. It's memoization. All right. So this was the contest. I think it was. Yes, it becomes much simpler with this approach. I did it more complex in the contest. Yeah, I mean, yeah, sometimes. So I didn't do the contest. I did it afterwards. So maybe that helps think more slowly and figure out a good way to do it. In the rush of the contest, whatever works, it's good. So yeah, I think that's all. I think it was on the easy side. Yeah. Compared to other contests, especially Q4, given that it had a very short and sweet solution. Okay, so yes, this is all I have for now. So I'm back, and I'm gonna be doing more streams in the future, so stay tuned. All right, so see you in the next one. Thank you. Great stream. Thank you. Thank you both for the support. See you on the next one. Bye-bye.